So in this video we'll be talking about solids, liquids and gases and changing state, so that's changing from a solid to a liquid to a gas and so on, and the energy changes involved when we change state. Once you've watched the video or during watching the video, you need to take class notes. So you need to make sure that your class notes are up to date on this topic, ready so that we can do questions together in the next lesson. Remember, you can use the pause button to pause the video so that you've got time to write notes. So, solids, liquids and gases. You should be aware of the particle model for solids, liquids and gases already. You should have already done it at lower school, whether that's in physics or in chemistry. In a solid, we know that the particles are arranged in neat rows and columns and they're all touching each other. In a liquid, we know that the particles are touching each other, but they're randomly arranged. And we know that in a gas, the particles are not touching each other, they're really spaced out, and they're randomly arranged. Now we can use this model to explain the differences in density between solids, liquids and gases, and we've already looked at how we calculate the density of solids and liquids, and we can talk about whether the particles are touching or not touching, and whether they're neatly arranged or not, to explain why the density of solids, liquids and gases is different. An important thing to start thinking about now is that we know, hopefully, that if we change from a solid to a liquid, we call that process melting, and that if we change from a liquid back to a solid, we call it freezing. But what we need to think about is what energy changes are taking place. So a solid has less energy than a gas in terms of the energy that the particles have. So we've got increasing energy from a solid to a liquid and then from a liquid to a gas. So if we want to change a solid to a liquid and we want to melt it, we need to add energy to the system. And if we want to change a liquid to a solid, by freezing it, we need to take energy out of the system. The same with boiling and condensation. To turn a liquid into a gas, that means that we have to add energy to the system through boiling. And if we want to change a gas into a liquid, we need to take energy away by condensation. Now we call this process of changing from one state of matter to another, so from a solid to a liquid, for example, changing states. And it's worth mentioning now, because we're talking about the energy required to do that, that heat energy or internal energy only travels from hot areas to cold areas. It can move from hot areas to cold areas by 3 different ways: conduction, convection and radiation. And the bigger the temperature difference between the hot place and the cold place, the faster the rate of energy transfer. But heat energy only travels from hot regions to cold regions. Now if we look at changing states in a bit more detail, we've already talked about this idea, or brought in this idea, that we're going to change the energy. Okay, so we have to, if we're going to move from a solid to a liquid, we need to add energy to the system and melt it. And if we're going to change the liquid to a solid, we have to remove energy from the system so it can freeze. What's worth remembering is that the temperature at which these changes of state happen is affected by impurities. So if you added salt to water, you change its melting point and you change its boiling point. Now remember that changing state is a physical change. So if we change from a solid to a liquid, that's a physical change, and they are reversible. I can change from a solid to a liquid, and I can change back from a liquid to a solid. They are reversible. Unlike chemical changes, so in chemical reactions, the ones that you see in chemistry, those are chemical changes, they're not reversible. But physical changes, changes of state, are reversible. The other thing that's important to remember is that when we change a solid into a liquid, mass is conserved. So if I started with 10 grams of ice and I melted it, I would have 10 grams of water at the end. Mass is conserved. However, as we mentioned earlier, that 10 grams of ice and that 10 grams of water may well have different densities because of the particle model. So, what we're going to look at now is a graph of what happens to a substance as it's heated over time. So whenever we're faced with a new graph, the first thing we have to look at is what the axes of the graph are. So on this graph we've got temperature here on the y-axis, and we've got time here on the x-axis. So we've got a substance, we start at 0 time here, it's heated over time, and we've measured what happens to the temperature and plotted that as a graph. Now this graph is for ice, water and water vapour, but this shape of the graph can apply to all substances. So to start off with, we start at time 0 and we heat up, in this case, some ice or a solid. The solid will heat up and steadily rise in temperature until it reaches its melting point. Here it reaches its melting point. The solid will then start to melt and turn into a liquid. At this point there's no change in temperature. So all through this point here we have a mixture of solid and liquid as the solid is melting, but there is no change in temperature. Then we get to here, and here all the solid has finished melting and turned into a liquid. And so as the liquid is heated, the temperature rises again steadily until the liquid reaches its boiling point. At this point we then have constant temperature again as the liquid changes into a gas by boiling. Okay, so there is no temperature change here. It's still being heated, but there is no temperature change. Eventually all of the liquid will have boiled and formed a gas, and then we just have gas, and this gas is still being heated, and as it's heated its temperature will increase. Now, a couple of really important points to mention again. First of all, these boiling points and melting points will be affected by impurities, so I can change where these points are by adding impurities to the substance. Secondly, there is no temperature change while the solid is melting into a liquid and while the liquid is boiling into a gas, even though the substance is still being heated. Okay, throughout this whole process here, energy is being added to the system. It's being heated up constantly over time, but we don't get temperature increases all the time, only at certain points, and that's what we're going to look at in more detail now. So the question is, why is there no temperature change here and why is there no temperature change here, even though the system is being heated, energy is being added to the system? And we have to think about what the energy is being used for and what needs to happen in order for something to change from a solid into a liquid, in this case here. Okay, so if we think back to our particle model of a solid and our particle model of a liquid, we know that in a liquid the particles can move around a little bit more, they can vibrate a bit more than they can in a solid. They're freer, and so the solid here needs energy to break the bonds between the particles in a solid so that it can behave like a liquid. That process of breaking the bonds between the particles requires energy, and all of this energy here isn't going into increasing the temperature, it's going into breaking those bonds. We've got the same thing going on here when we change a liquid into a gas. The energy being added to the system isn't used to heat up the liquid, it's used to break the bonds between the particles so the particles can escape as a gas, and so there's no temperature change. Now what you have here is a number-coded description of each part of the previous graph that you saw. So for section 1, where the solid is being heated, section 2, where we've got the latent heat of fusion, which is a posh physics term that we're going to learn about in the next lesson, for melting, section 3, where the liquid is heated, section 4, latent heat of vaporization, again we're going to learn about that more in the next lesson, and then section 5, where the gas is being heated. Now, we talked in our previous lesson about specific heat capacity, and you completed a practical to find the specific heat capacity of different metal blocks. And we used this equation here. Energy added to the system is equal to the mass of the object times its specific heat capacity times the temperature change. And we said the specific heat capacity, C, was the amount of energy required to change the temperature of 1 kilogram of the substance by 1 degree. So if we have a bigger mass, we need more energy, and if we have a bigger temperature change, we need more energy for a given substance. Now, what's important to remember here is this: we can use this equation to calculate the energy we need to add to the system to increase the temperature of a solid, or to increase the temperature of a liquid, or to increase the temperature of a gas. But we don't use this equation when we're to work out the energy that we need to change state. So we don't use this when we're changing state from a solid to a liquid, or from a liquid to a gas. We only use this when we're heating a solid, or we can use this when we're heating a liquid, or we can use this when we're heating a gas, not when we're changing state. So if we go back to our graph and our particle model, we can use the specific heat capacity equation here, we can use the specific heat capacity equation here, and we can use the specific heat capacity equation here, but we can't use it here and we can't use it here. So we could calculate the amount of energy added to this solid here to get this temperature change, and we can calculate the amount of energy added to this liquid here to get this temperature change, and the amount of energy added to this gas here to get this temperature change, but we can't use the specific heat capacity equation here or here. Now it's quite nice looking at the graph with the particle model underneath. So you can see here we've got our solid and it's been heated up, so the particles are going to vibrate more, and then eventually they'll have enough energy to then start melting and behaving like a liquid, and eventually all of the solid will have changed into a liquid because it's had energy added into it over time, and then the liquid will have more energy added to it, and so the particles can move around more, and then it will reach its boiling point, and some of the particles will have enough energy to leave the system and become a gas. And if we keep adding energy, enough energy here, then all of the particles in the liquid have got enough energy to turn into a gas. Remember that as we go from a solid to a liquid to a gas, we've got increasing energy. We have to add energy into the system, but also remember these are physical changes, it's a reversible process, so if we took energy away from the system, we get exactly the same graph over time, but just in reverse. So, what to do next? Make sure your class notes are up to date, but you don't need to repeat anything that I've repeated to make sure things are clear. Bring a list of questions to the start of the next lesson so that we can talk about them if anything hasn't made sense. I'd like you to start thinking about the difference between evaporation and boiling, and we're going to be talking about this in quite a lot of detail in our next lesson. And I would love it if you could bring some feedback on how you found the video and what would make it better or easier to use, or what you would find helpful. Thank you.